So yes, today Martijn and I are going to be presenting some work we have been doing last year, investigating the TE of the Samsung Galaxy S21 of the Exynos model, and especially a component of this TE, which is called the loadable firmware. So why are we here? Well, there's a couple of reasons why we are here, and some more, and a couple more, and a few more, and some more that are still in the disclosure process. And we're going to talk about a couple of these things. This is an overview of what we're going to talk about. We'll first have an introduction about TEs and TRUSTZONE. Then we will be talking about Samsung's TE architecture, which is based on their own TOS, which is called TEEGRIS. Then we will be looking at loadable firmwares, which is most of the analysis we'll present, how we extracted them, how we decrypted them, and then how we found vulnerabilities inside these firmwares and how we exploited them. So let's start with an introduction about trusted execution environments. This is like a TRUSTZONE-centric view of TEs, where basically the environment is split between two worlds: normal world, which is the RE, rich execution environment, and the secure world, which is the TE. And in the normal world, you have the usual applications and Android environment running, while in the secure world, you'll have a TOS, which runs the kernel, several trusted applications, which ultimately will protect keys, such as payment keys, file system encryption keys, but also biometric data belonging to the user of the phone. Let's look at TRUSTZONE a bit more in detail. We have the split between normal world and secure world that I just showed. And then you see in the columns different privilege levels defined by the ARM architecture. So we have EL0 in both normal world and secure world, which is the application level, so it's the least privilege level. Then we have EL1, which is where the kernel run, both the Linux kernel and the TEEGRIS kernel in the secure world. We have the hypervisor in the normal world. And finally, at EL3, which is the most privileged level, we have BL31, which is also called monitor code. And this is some dedicated code that always runs in secure mode and handles the switching between the two worlds. We see that the secure world is an isolated part of a system, so it has this NS bit, SER NS bit set to 0, NS means non-secure, which means if a secure world performs operations over secure memory or secure peripherals, they will be allowed. And if instead these operations come from a normal world, which has the NS bit set to 1, these will be blocked. So if we look at how applications will interact with the TE, you'll see that first thing the app needs to do is to send a request to the kernel. And that's because Android apps cannot directly interact with the TE. This communication is done through some device that the Linux kernel will expose. And then the Linux kernel will execute this special instruction, which is called SMC, Secure Monitor Call. And this SMC will come up multiple times in the course of this presentation. This is an instruction that will generate an exception at BL31, so at the EL3 level. And BL31 will then determine the ID that was specified by the app for this SMC call, and it will decide what to do. You can either process it internally, or it can forward it to a trusted application through the TEEGRIS kernel. And the trusted application will then process this and use functionality implemented in the TEEGRIS kernel, and then start to do the inverse path and send the answer back to the application. So TEEGRIS is a TOS that has been developed by Samsung. It's been deployed on the S10 for the first time. It's stored encrypted in high-end models. It's a relatively small kernel, but it's not a full microkernel, so it still contains a couple of drivers. It conveniently implements POSIX like syscalls, so whenever you want to interact with a driver, you'll need to open a device, and then you can do the usual IOCTL, read, write, mmap, etc. to interact with them. And these are some examples of drivers that are implemented in the OS. Now, if we go back to the previous picture, there's actually something I didn't show before, which runs next to the TEEGRIS kernel, and these are the loadable firmwares, which is what we are going to look at today. So the idea of a split between kernel and loadable firmware is that the kernel tries to be somehow hardware agnostic, and the loadable firmware implements all the low-level, like register, peripheral operations that are hardware-specific. And so how are these components loaded? So this is a boot chain of S21. It's a fairly typical boot chain. So we'll have first the boot ROM that will start the chain of trust. It will then load BL1 in secure mode. BL1 will run from SRAM and load the next stages, so EPBL, which, and as you can see from this box, basically all the next stages that run in secure world are stored encrypted, both in flash and in firmware updates. So basically this is a bit of a black box for an attacker, and from this point on you will have both secure and non-secure worlds running in parallel. The non-secure one will have first BL2 and then little kernel, which will then bootstrap the Linux kernel. And on the secure side, you instead have EPBL, which loads BL31. So BL31 is this monitor code that is always running at runtime. BL31 will then get images for loadable firmware and TE from the little kernel. It will authenticate, decrypt them, and load them into memory. So if we look at the loadable firmware, they are stored in a specific partition for loadable firmwares, LDFW. It's actually a single image that contains many concatenated smaller images for each loadable firmware. So there are multiple loadable firmwares. Each of them start with this magic loadable. And basically the BL31 will iterate through all of them until it finds an image that is called tail firmware. When that is found, it means it's the end. And yes, they are loaded at a base address 100,000 in X. And as I mentioned before, they all run in secure EL1. So they are very privileged as the kernel, and they're an interesting target for an attacker. So as I mentioned, there are multiple loadable firmwares. We're going to list them here from the biggest to the smallest. This is the crypto manager. It has a lot of code because it has to implement all the cryptographic functionality that is done by the hardware. It does stuff such as encryption and decryption using the hardware key, random number generation, OTP fuses, and so on. Then we have a DRM loadable firmware, which is used for trusted UI for payments, so when you enter your PIN. Secure camera for face unlock, and secure video path for DRM. We have the flash memory protector, which is done for transparent flash, used for transparent flash encryption. HDCP, which is the cryptographic component of HDMI. And RPMB, which is some form of secure storage that is implemented on the flash. So if we now extract one of these loadable firmwares from a firmware update, we can take a look at what's in there. We see the magic, as we mentioned earlier. This is the size. All of the values are in little endian, so the size would be 211000. Then there's SMC base, and this is interesting. So basically, each loadable firmware has a SMC range assigned. So every SMC has an ID. In this case, the SMC base for this loadable firmware is 82001000, and then the last byte is ignored. So basically there will be a pattern match on the first 3 bytes. If the caller specifies those 3 bytes as the SMC value, they will be forwarded to this loadable firmware. Then next one is just a version number. It's actually a date. So in this case, it was the 29th of December 2020. And then there is a name. So this is the crypto manager. It's the largest loadable firmware we mentioned earlier. And finally, at the end, there is this huge block of encrypted code and data. Of course, the real device is much larger, and it's just, yeah, basically encrypted. You can't do much with it at the moment. So let's take a look at how loadable firmwares look like when they are loaded in memory. So they have a very simple memory view. Basically, this is the lowest 32 bits of the memory ranges. And then at address 100,000, there will be the image of the loadable firmware as stored in flash, but of course decrypted and then stored into memory. And then at this address, there will be all the registers that are supported by the SoC. And then at the address 80 and then all zeros, that's where the DRAM starts. So this will be the 2 gigabytes of DRAM mapped at this address, which includes the DRAM configured as secure. So this is DRAM which is reserved only to the TE, and it contains also another copy, a sort of alias of the loadable firmware as viewed in the physical memory. So now if we go even more into detail, we see there is this, on the left there is a header of the loadable firmware, and at address at offset C there is a pointer to the function that is used to handle SMCs. So it will point here. So whenever BL31 will receive an SMC that matches the ID, which is stored here, of this loadable firmware, BL31 will read the address at offset C, and it will then call this function to process the SMC. And inside, these loadable firmwares will have SMC handlers, which is normally just a big switch, which takes 5 arguments. The first 4 of them are simply the 4 registers from X0 to X3 that were passed by the caller, where we invoked the SMC. The first one is always the SMC ID, and the remaining 3 are specific and their meaning depends on the SMC. And then you'll have all the handlers. In this case, it's the handler for SMC 3806. Then there is the 5th argument, which we called is_nsec, and this specifies whether the caller was running in secure or non-secure mode. So what this means is that all these loadable firmwares have a way to identify who called the loadable firmware SMC, and they can decide whether a certain SMC is only allowed to be called by the TE, like it is in this case, or if it is allowed to everybody. So even the RE would be allowed to invoke certain SMCs. For now, let's take a closer look at the secure-only SMCs. So the idea of secure-only SMCs is that they will be called by the TEEGRIS kernel. And the TEEGRIS kernel runs the DL1, so it's the same privilege level of loadable firmwares. However, TEEGRIS implements some more functionality, and this is an overview of the TA permissions. And we can see one of the permissions that TA can have is the permission to issue SMCs. So, of course, SMC is, just by architectural definitions, a privileged instruction, so TAs cannot directly use SMC instructions. But the kernel has an interface exposed to SMC. That's what we were seeing at the very beginning, like some drivers that are accessible using the POSIX syscalls. And TAs that have these permissions, and there are a couple of them, can call this this driver and then pass SMCs to the loadable firmwares or to BL31. And this is actually a decompiled view of this SMC handler as exposed by TEEGRIS to TAs. So assuming a TA has the correct right for talking to to issue SMCs, the first thing the kernel does is validate and parse the SMC arguments. This is not very interesting because the TA can always specify a combination of arguments that says do not validate and do not check any of them, just pass them directly to the SMC handler. And if that function succeeds, then the kernel will forward the arguments and issue the SMC. So we started thinking, let's assume we exploited a TA. We have runtime control of a TA. What can we do with this SMC interface exposed by the kernel? And getting runtime control of a TA is not something we will be talking about today. TAs are just applications. They have a usual set of mitigations, and I mean, vulnerabilities happen, they can be exploited. So if we have such a vulnerability, what can we do with it? And 2 years ago, Martijn and I also looked at the S10. And back then, we identified a vulnerability that gave us full control of the TE, which means thanks to this vulnerability, we were able to extract the loadable firmwares from memory as they were running on the S10. And our idea was, can we identify some functionality that has not been changed in the S10 in the S21 compared to S10, and try to exploit this on the S21. So this is what we identified. This is an SMC implemented in the crypto manager, and this is only reserved to the secure callers. And the first thing it does, it takes an argument passed by the caller. This is a structure of C0 bytes, and it checks that this structure needs to be fully within the TE memory. And with TE memory, I mean anywhere in TE memory. It can be TA memory, crypto local firmware memory, kernel, TEEGRIS kernel memory, anywhere. Once that is verified, it will then extract two physical memory buffers as specified within the structure. So basically the structure will have a physical memory start address and a length of the first buffer and of the second buffer. And again, it will check that these two buffers are fully within the TE memory. After all these checks are done, it will call some hardware functionality that will do an encrypted DMA from first buffer, encrypting data into the second buffer. So is there a problem here? Well, it's good that the SMC verifies that all the buffers are in the secure world, but there is no, as I mentioned, there is no check that these two buffers are within TA memory or within TE memory. It's just simply somewhere in there. And it sort of expects that these parameters are set correctly by the caller because it expects the kernel to set these parameters correctly. But what if instead the TA specify a different value for these parameters and passes them through the TA interface? And this is actually our plan. So the idea was use this SMC interface to the kernel to issue an IOCTL. The kernel will simply take our data, forward it to BL31, which will see, okay, there's an SMC coming from the kernel, and it's for the crypto manager. So it will simply, again, pass it to the crypto manager. The crypto manager sees, okay, this is the SMC used for encrypted memory-to-memory DMA. And then it will configure the crypto engine, set up the mode, which is encounter mode. And this is actually the only thing that is enforced by the crypto manager, because all the rest, key, IV, source address, destination address, and length will be controlled by the TA. Once the crypto engine is configured, what we can do from a TA is, for instance, point the source address from crypto manager memory and destination address in some memory belonging to the TA itself. And because we know the key, we can simply encrypt memory, put it in the TA memory space, from within the TA decrypt it, and then we extracted memory belonging to the crypto manager. And we're not limited to the crypto manager. We can extract BL31 memory, we can extract kernel memory, everything, just copy it within the TA and then read it out. We have only a small problem left, and it is that the SMC handler and the DMA engine expect physical addresses, and the TA has no idea about physical addresses. The TA runs in its own virtual address space, and we need to find a couple of physical addresses. One is the physical address of the structure that contains the definition of the buffers, and the rest is the physical addresses of the buffers themselves for doing the DMA. Fortunately, this is not too complicated because there are a few things that we know. First thing we know is where the TE memory starts and ends. This is just something you can read out from Android. And then we know that heap allocations are relatively predictable. So we know TA can allocate at max about 50 megabytes, and this whole space is 120 megabytes for the TE. We know that if we have a big allocation, contiguous pages in the VA space will be also contiguous in the physical address space, so that's nice. You get a nice contiguous view. And the start address of this allocation, and I mean the physical start address, is more or less constant. So there are a few pages that differ between different executions, and I think these mostly depend on just the state of the TE memory at that time. What we thought was let's spray the heap, let's put thousands of copies of this structure and execute this SMC from a ROP payload that runs in a compromised TA that has the SMC permission. So once we do a big allocation, this is what's going to happen. We will allocate something on the heap, and these are the start and end address plus minus a few kilobytes of allocated heap structure on the heap. And then we'll start filling this structure, space on the heap with a lot of copies of the structure, and all these copies in the structure will set a destination address at somewhere close to BBD00000, because we know the destination address, that destination address belongs to the TA, and the source address to other memory areas that are outside the TA memory space. Then we issue the SMC, and then this whole buffer that we allocated will be overwritten with encrypted, extracted TE data that we can decrypt offline. And we tried this approach, it worked. And the nice thing about this approach is now I presented how we managed to read out protected memory from the TE kernel, but we can also overwrite it. And because this happens through a DMA engine, you're not restricted by the MMU settings that normally would prevent you from overwriting code and so on. With this, you can simply tell the DMA engine, write this on top of the code section of the kernel, and it will happily replace the kernel. So this was the first vulnerability we found, which is nice, but can we find more? And so at this point, we were at a stage where we had the loadable firmwares fully extracted. We decrypted them. We got their plain text value, load them in IDA. And the SMC we currently exploited is only accessible to secure memory, which means you would first need to exploit a TA, which has the SMC permission, then run your code from there, and then run the exploit, which, I mean, it's quite complex. And we thought, is there something that we can do directly from the Android side? Because as we showed earlier, there are some SMCs that are accessible to Android. This is not so simple, though, because it's not easy to issue arbitrary SMCs. As I mentioned, SMC is a kernel-only instruction, and in the running system, in S21, there is no driver that exposes this functionality. Even if you're rooted, there's no driver that just takes your SMC ID and passes it happily to the TE. So for the purpose of this research, we decided, okay, let's just make a custom kernel where we can flash on the device, and we added two drivers to it. One is an SMC driver, which does exactly what I just mentioned, takes SMC ID and some arguments, and then just passes them to the TE. And the second driver is a sort of helper driver that we used to access physical memory from the Android side. It basically maps physical memory and then allows user mode application on Android to read and write the contents of this physical memory. So now that we have the setup ready, we started looking for vulnerabilities. And I would now like to ask Martijn to come over to tell us a bit more about these.
So what can we find? Because these are encrypted binaries, right? And it sort of means that this also means that not that many people are looking at these type of binaries. So could that maybe reveal interesting vulnerabilities? So let's start to have a look. So we start with looking at the RPMB loadable firmware. And what it does is, one of the first things you need to do is you need to register some memory that you are going to share between the secure and the non-secure world. And somewhere during the boot process, you will, the Linux kernel will issue an SMC to say, like, this is where I want to have this shared memory. And what this SMC then will do, it will check like if this memory is fully in non-secure memory, because, well, you don't want the Linux kernel to maybe provide a pointer somewhere in your secure memory, so it will do a range check like, hey, is this really non-secure memory? And if so, it will register it and it will set up the context for the RPMB loadable firmware. So this works as expected. But then we started looking, and we noticed that there was some new code added that was not there at the S10 yet. And this code was remarkably small. It was basically 4 lines when you decompiled it. And that's a bit odd. Especially it means that we are for sure not checking where this call is coming from. So everybody can call it secure or non-secure side. But what's even weirder, are we really directly writing to some pointers that are provided by the caller without any pointer check? And the answer is yes. So we have now a primitive, a directly reachable primitive from the non-secure side, that we can write a 64 or a 1024 to any address we want. So how can we use that? Can we maybe corrupt a length from a buffer or from a range check to maybe create a buffer overflow? Can we maybe do some magic with maybe the page tables? Well, we decided to take a slightly different approach. We decided to actually let the hardware and use it basically against itself. So how is it actually working that we have a separation between a non-secure and a secure world? How is the memory from the secure world actually guaranteed not accessible by the non-secure world? Well, your CPU core is running either in secure mode or non-secure mode. And this is controlled by the NS bit that is part of the STR register. And when the CPU wants to access some memory, it will put a memory transaction on the bus. And this transaction will then get routed to the memory controller. And as part of this bus information, we send the address, but we also reflect our execution state on the bus. And then this will reach the memory controller, and the memory controller will then access that address for us. Except there is, in reality, one step happening in between that is going to check, like, is this actually a secure or a non-secure memory access? And the hardware that is doing this is called the TZASC, the TRUSTZONE Address Space Controller. And the TRUSTZONE Address Space Controller figured through the hardware registers something called secure ranges. These are a group of start and end addresses with permissions, with what the hardware will consider as memory that has a special, that has special permissions. And this could, for example, be it is accessible by the non-secure world, or it is accessible by the secure world and not by the non-secure world. And then what the TZASC will do, it will basically compare the memory transaction against the secure ranges that are configured. It will check the execution state, and it will decide whether or not it will allow it. In this case, we are doing a transaction to something that is part of the secure memory while we are running in the non-secure state. So in this case, the TZASC will just say, this is not going to happen, and it will generate an interrupt for a security violation. However, if we are actually running in the secure mode, the TZASC is going to allow the memory transaction to happen. But how is this actually really working from a hardware level? So how are these secure ranges configured? Well, there are standard designs for TZASC, and some vendors use these standard designs. They license from ARM directly. However, Samsung has decided to create their own controller that is functionally the same, but the register interface is completely different. And what you see is that when you start checking the registers, this is not documented, so we had to figure out where these registers are and then start looking like, what is the meaning of all these bits? What you then at a certain moment see is that we have two blocks of 30 bytes in the register space that looks an awful lot like, hey, this could be a start and an end address, and we see some other bits, which are probably permissions. So what do we have here? Well, in this case, we have a start address from B8A00000 to BFFFE0, which is actually one page less than what it is really protecting. And actually, this is even a simplification. In reality, we don't have one memory controller and one TZASC, but we have 4 memory controllers and 4 TZASCs, because Samsung decided that it is sort of interleaving the memory. So every 256 bytes of memory is routed to a different memory controller. So depending on the address you want to access, it will go to a different controller and a different TZASC, and also each TSC has its own set of hardware registers that configures what the secure ranges are. Well, let's start messing with these registers. What happens, for example, if we set an end address before a start address? Well, you would assume that this will completely brick the system, right? It's for sure, this is not a valid configuration. Well, you start trying this and maybe you see some interesting behavior. So, for our SMC driver in the Linux kernel, we have created a very small command line utility that allows us to interact with the driver, and we can just from a shell, an ADB shell, issue arbitrary SMCs with arbitrary arguments, which is very convenient from a research perspective. So we provide the SMC ID that we want to call, and we provide the hardware register address of the end address of the secure range for the TE memory. And we do this once for every TZASC, because we have 4 of them, we do it 4 times. And you actually can see that the end address, the 3rd byte, is basically incrementing. That is the shift of where these registers are mapped. And then our tool will do simply an IOCTL with the arguments, provide it to our driver, put it in the right registers, and issue the SMC instruction, because, well, from user mode we cannot issue that instruction directly. And when you then check back, like, what has happened, well, the last one was writing 1024 to the end address. We still have the correct start address for our secure range, except this time the end address has been changed to 1024. And, well, we no longer have a valid configuration anymore. But what is now going to happen when we access secure memory while we are running in non-secure mode? So with the NS bit set to 1. Well, from the TZASC perspective, we have a secure range, but a secure range with an enter address before the start address. And the TZASC is just like, okay, I'm going to allow this. Fine, go ahead. And this is exactly what we are going to do. So, I have here an S21 with the firmware from May last year. That is the one that is still vulnerable. And first I'm going to show you a part of First I'm going to show you a part of secure memory. And we have nothing done yet, which basically means we read back zeros. At the moment our request is being ignored. And what we then can do, we issue our we issue our 4 SMCs. So you can see that it is actually for convenience printing all the register states before and after for debugging purposes. But we have now 4 times issued the vulnerable SMC, and let's check the secure memory again. Well, we have actually unprotected the BL31 memory, well, the entire secure memory, but this is the place where it stores its version number. Basically showing we have now, from the non-secure side, completely unrestricted access to the secure memory. So, what else can we find? Well, let's take a look at a completely different loadable firmware. So we had a bit more looking at the RPMB one. Well, we decided that after a while we wanted something else. So we started looking at the HTCP one. And the HTCP one is a bit interesting. So for some reason, it allows you to configure an interrupt ID, which is somehow associated with how they handle the secure communication with the end device. But the non-secure world is assigning which interrupt is being used for this, or at least saying to this loadable firmware, this is the hardware interrupt you have to use for this. So we have an SMC that allows us to specify this interrupt, but then we have another SMC that is going to configure this SMC in the hardware. So what we will do is we will change in the GIC, the generic interrupt controller, that is basically a configurable mechanism for how you want to route your interrupts, and if you want to route them to the normal world or the secure world. And we are going to change this based on the interrupt index we have specified by the normal world. Except we don't do any form of validation on it, and we directly access the relevant hardware registers. So what allows us to do that? Well, because we are adding this interrupt index and we calculate which hardware register corresponds with a certain index by masking and shifting the index, we actually get a write primitive in a part of the register space. Well, actually, it's sort of the entire register space except a small part at the very beginning. What we can do with this is from 4 bytes, we can selectively set 1 bit to a 1. We can decide which bit we want to set, but it's only 1 bit. So what can we do? A bit of a challenge with this is that we don't really have a very deep understanding how all the hardware registers work, right? It's not like that for SoCs like this, that the register documentation is freely available. So what you want to do would mean full reverse engineering, and of course things like Linux kernel drivers can be very convenient for it, but we want to have something that has an impact from like the secure side. And basically meaning things that the Linux kernel can access are probably not interesting from this perspective. So what are we going to override? Well, we decided to just go for the TZASC again. It's within range, but this time we actually set the high bit of the start address of the secure range, effectively setting the start address after the end address, again unprotecting the secure memory. So, how are these loadable firmwares actually loaded? Because, well, they are stored in a separate partition. We have seen during the boot flow that they will get loaded by BL31, actually in collaboration with little kernel. So how is this actually working? And we started working on trying to reverse engineer this mechanism and try to get an understanding how this encrypted blob of data is loaded and authenticated. Maybe something interesting is going on there. Well, what happens is little kernel is doing the load from the UFS, puts it somewhere in non-secure memory, provide the pointer through an SMC to the secure world, to the monitor BL31, because that's the one running at that moment. And then that SMC will trigger the signature verification, the unpacking, the decryption, put it at the right location in the secure memory, configure or triggering an initialization mechanism. However, this SMC, is this only accessible during boot, or is there maybe something interesting also during runtime? Well, this is the SMC. This SMC in BL31, it does the pointer check, so you provide non-secure memory. It will copy in that memory from the non-secure side to the secure side, because, well, while it is unpacking it, you don't want that the non-secure side can mess with it and maybe cause some issues, like some Tocto issues. And then it will do a signature verification, either directly in the in BL31 itself, or if you have already loaded your loadable firmware before, you can actually load it again, and then you will verify the signature using the crypto manager. And if something fails, you will erase the secure memory. So this is, of course, a separate buffer, right? So you maybe don't dynamically allocate it, but during development, you have said, okay, this is the buffer where I'm going to load my loadable firmware. Because, well, if you can load it again, that's probably not the best idea. Well, is it actually a separate buffer? So what happens if we try to send the SMC, even with just a blob of 0 bytes? Well, we have the phone. Let's try. So the phone is still, the secure memory is unprotected. Sure, we can directly poke in it, it's not relevant. So let's fill some random location in non-secure memory with null bytes. Phone is happily. Let's then actually trigger the SMC. Where did I trigger? Well, the phone instantly became unresponsive, and we can actually see the SMC. In the previous SMCs, you saw it returning and printing like the register state after returning. In this case, we cannot even get to that point anymore. So what has happened here? And you will hear a beep in a moment because, well, the crash is silent and the hardware watchdog needs to kick in a moment and will restart the phone. So, what happened? Well, this was for sure not a separate buffer. We were directly stamping over the memory where the loadable firmware is currently running from. Of course, this is like an encrypted blob of data, an assigned blob of data. And we are going to verify the signature. And this signature, unless we of course reload the original loadable firmware, this signature is not going to match. We cannot force signatures. And when we fail the signature verification, we're also going to zero out that part of the memory. We have already filled it with zeros now, it doesn't really matter. But you have seen what happens with the phone. So either because we directly fill it with zeros, or you try to put there some real code, it will zero it out, the phone will crash within a fraction of a second, because those loadable firmware are in use. So how can we prevent this zeroing out of the after the signature verification fail? Can we somehow bypass the signature verification? We can maybe raise it. So the signature verification, it's quite a significant amount of code and data that needs to be verified. It will need to hash it, it will use the crypto engine for it. It's relatively fast, but we can probably raise it. Or is there maybe an easier way? Because remember, we had two ways of verifying this signature. So if you load the loadable firmware for the first time, we were verifying it using BL31. But if we had the loadable firmware already loaded, we were verifying it using the crypto manager. And the crypto manager is a loadable firmware. So if we overwrite the loadable firmware, what code is doing the verification? Well, actually, we have replaced that complete underlying code by overwriting the blob and trigger the authentication. We actually automatically also trigger jumping to the data that we have written there. So basically the only thing we have to do is the authentication SMC, make it return, yeah, this signature is perfectly valid. And you can completely replace the loadable firmware at runtime. It will not be erased. And now it's our code running as loadable firmware. What else do we have? Well, every system needs debug information. If there is something that developers love, it's debug information. And, well, I love debug information as well. So if you check after you boot up and you grab the DMesh of your S21 or basically any Exynos-based phone, you will see messages of something called the sec log. And this is really doing what its name implies. It is getting the messages from the secure world and putting them in the non-secure DMesh of your Linux kernel. So we have, for example, seen About the RPMB, the initialization, we register some world shared memory. The non-secure side provide the address where we want to have this shared memory. Well, the loadable firmware is nicely saying a message, I have registered your shared memory, and here you can find it. Well, how is this actually working? Because how is it possible that something from the secure world can write to the kernel log on the non-secure side? Well, this mechanism, the secure log, is basically a set of ring buffers that are shared between the secure and non-secure side. And we have then a kernel driver running in on the Linux side that basically takes the data from this ring buffer and will then kprint them to the kernel log, and that way this is how they show up in DMS. For, I guess, convenience, we have per CPU core a separate ring buffer, probably also to not have too many issues with concurrency locking and similar kinds of problems, which can get a bit hairy if you have to do it across a security boundary. So we have here our SMC handler, we register our message, and we call, well, we have called it printf, we have no idea how this function is originally called. What is shared in our ring buffer is defined by this structure. And what we have is basically a write counter, a read counter, a base address, and two flags. So one of them is like the buffer is full, so the Linux kernel was not fast enough in picking up new messages, and something about that the system got blocked for whatever reason. Well, of course, we properly validate this information, right? Because we share it across the security boundary from the normal world to the secure world. Both the normal world and the secure world are dealing with this information, changing the read counter, changing the write counter. This is perfectly validated, right? So let's take a look at how printf is actually implemented. We start with, based on which core we are running, getting the address of our ring buffer. And in log info, we are now pointing directly into memory that is non-secure. And what do we get from that? Well, we get the write counter, because, well, we are going to add messages to the ring buffer, and we have our base address. And then we calculate, based on the write counter and the base address, where we are going to write. And we write the message there. But what is missing? Where is the check that we don't specify an overly big write counter? Where is the check for the base address? Well, it's not there. So the ring buffers are at C3 000000. One for each core. They get incremented addresses by roughly 10,000 hex. We use our driver to directly poke in that memory. And what we basically do is we set both the read counter and the write counter to 0. So effectively the ring buffer is empty. And we change the base address where the log message is being written to. Well, I don't know if you recognize this address, but this is the TZASC. One thing, we need to be quickly restore it. Strictly speaking, it's not needed. You can also unload the kernel module. But if you don't want to mess too much with the system, if you quickly restore the original information, you have a pretty high chance that you are not crashing the system. At least as long as you are not doing it too early after boot, because then the system is still quite actively writing messages to the seglog. One thing, the ring buffers are core specific, so we need to pin our process to a specific core, or we need to change all ring buffers. Well, the phone rebooted from the previous demo, which is exactly why that was a crash demo and not something else, because otherwise I would forget to reboot it. Look. Oh, I forgot to show you. that we cannot access the secure memory yet. Well, you have to trust me on that, because what you can see is we have only protected one TZASC this time, not all 4 of them. We can simply repeat this 4 times and unprotect all of them. What we could also do is, we have access to a quarter of the secure memory code and data, so we can also simply change the code of a few SMCs that are exactly within this quarter of the memory that we have unprotected, and that way further compromise the system. Well, that brings us to the end. The loadable firmware is really critical in Samsung security model. It is so privileged, and also this attack surface is not only on the secure side, it's actually both to the secure side and the non-secure side. Of course, you need kernel level privileges to reach this SMC instruction, because, well, by default, there is no driver going to give you that. I'm not sure that for this audience that's an unovercomable obstacle. We found some critical vulnerabilities. We have a few more in the disclosure process. And what is particularly interesting is actually the simplicity of these bugs. The obstacle is that this is encrypted, not because this is some super crazy exploit that you need to study for I don't know how long on. It are relatively simple attacks. However, the barrier for actually getting to this is high, and that you notice that when you are looking at this type of code. And for the people that have Samsung devices, I would say update, and also keep your updates in the coming months. Anyway, that's the presentation. I hope you liked it. If you have questions, please ask them. Otherwise, feel free to come to us. We will be around for, well, the rest of these 2 days.